guarantee it. Good. Okay. Let's kind of pick up where we left off. We were talking about, one of the things is, so suppose you have, the splitting field polynomial, degree in polynomial over some field. Usually we think rational numbers. This polynomial is separable. If it's irreducible, separable degree n, then its splitting field is Galois, and it's got a Galois group. Well, the Galois group will actually be a transitive subgroup of Sn. Remember what transitive is. It means given any pair of things that you're permuting A and B, there's a permutation that takes A and B. Right. So last time we saw the transitive subgroups in order for the small ones, S2, only S2 is transitive subgroup itself. S3, it gives S3 and A3. S4 gets S4, A4, dihedral, cyclic, and then not all prime four subgroups of S4 work, only this kind of exotic one here. Notice that if you look at the element representations, it's pretty clear it's transitive. Because any I and J, there's one of the something in there that's Xi to J. And for S5, we have S5, A5, dihedral on the pentagon, cyclic at order 5, and the strength group, it's sometimes called the Frobenius group order 20. This is generated by this. There are isomorphic copies of this that sit inside of S5. This is where I quit because there's 16 transitive subgroups. It gets small again, 7, just like 5 here. By the way, notice that during one of these subgroups, you should always have S5, A5, or SN, I'm sorry, SN, AN, DN, and cyclic order. You're always going to have it. It's the full cycle. S8 has 50. And just to show you things get out of hand, S12 has 301 transitive subgroups up to isomorphism. So I'm going to specialize actually. This is a little bit more general, but we're going to quickly specialize this Q. Definition A5. Let f of x and k of x and suppose the characteristic of x like 2. K of about 2. Suppose that the degree of f is n and it has n distinct roots of some splitting field. Have separable and degree of f is n, so it has n distinct roots somewhere. And with the word separable, of course, I also mean irreducible. We're going to define take all roots and take their difference. Here, where These are the roots of f. Then the square of this is called the discriminant. Is square. So it's of course square. It's triangle. This is actually a useful piece for Galois groups of reasonably small degree. Here is the first kind of separator for this. Proposition. Let D be in K and delta D is in K, and delta is in K. If and only if the Galois group of F and when I say Galois group polynomial, this means the Galois group of splitting. Little f, okay. Well, that's what I mean by the Galois group polynomial, just take its splitting field. If the delta is in K, then the Galois group of F is contained in. So this discriminant can be used as a tool tell whether the Galois group is contained in AN or not. So for example, five, then possible Galois groups that's in, well, S5, A5, cyclic order 5, D5, and which are the ones that are contained in A5? See, you got the cheap one. Five is not. What about cyclic order 5? Yeah, but isn't a 5 cycle even? Right? So for example, yeah, it's kind of weird, right? Because odd cycles are products. So actually, everything in here is a 5 cycle for the identity. What about D5? Well, what does D5 look like? Inside A5, I mean, up to isomorphism. Well, 1, 2, 3, 4, 5. So one of the generators is 1, 2, 3, 4, 5. That's the rotation. What's the flip? It's the so what's it? We flip about the axis. Right, and you can actually check the stochastic relations, SRS, multiply that out, and get our inverse. Right? That's even, that's even. Yes. What about this one? These two are no. Right? S5 is fairly obvious because it's got the permutation 1, 2 in it. It's an infill. This one, 1, 2, 3, 4, is an odd product of transpositions. So this one's not contained in this time. So the upshot is, if you have a 5th degree polynomial, you have 5 options for the Galois group. This thing pretty successfully cuts it in half, right? If you know that del is in K, then I know the Galois group has to be one of these 3, A5, C5, D5. And if del is not in K, then it has to be either the entire symmetric group, or it has to be the Frobenius group of 20. So I'll leave that for an exercise. What you should do for this is just write down what del is. And remember, the Galois group acts on the roots of this, right? That might help you justify this. Example. For a cubic polynomial of this general form, if I give you a cubic polynomial, the discriminant is given by a squared b squared minus 4b cubed minus 4a cubed c minus 27c squared is 18ac. This is something that is, let's say, tedious, but not terribly difficult, right? Because well, it's R1 minus R2, R1 minus R3, R2 minus R3. So this thing has to multiply back and get this, you know what del is, you're patient, you can go through it, right? It's not hard, but it will make you weave a tapestry of the family, probably. So, for example, I have the following cubic polynomial. Let's take, oh yeah, this is the smallest discriminant. So if I have this polynomial here, then the discriminant, well, sorry, it's equal to, in this case, of course, A is, and I did this once for myself, A is 1, B is -2, C is -1. Right? Then A squared, B squared is going to be 4 minus 4B cubed is going to be plus 32. Minus 4A cubed C. That's plus 4. Minus 27C squared, that's minus 57. Plus 18 ABC, so that's going to be plus 36. And I hope I did this right. That's going to be 76, 74. Now notice this is a square. Or a cube, say, if this was considering solid. And so well, this polynomial, the Galois group of this, the splitting field is either the splitting field is either of degree 3 or degree 6. Galois group of this cubic polynomial is going to be either A3 or S3. This is a square, so I told you everything you need in Galois group of this section. Cyclic of order. I'm going to give you, so basically, I told you everything that you need to know if you're looking at cubic polynomials over simple. Right? Because in this case, your Galois group is only going to be, it's either going to be S3 or it's going to be A3. So you look at the discriminant, if it's square in base field, and it's A3. If, as is usually the case, it's not a square, then it's all S3. What about quartics? Quartics are more complicated. And with quartics, there are 5 options for Galois group. And so we're going to pick this apart based on that Klein 4 subgroup of S4. So here we're going to assume that and the characteristic K not be 2. F irreducible polynomial KX of degree 4. With the staples in school. So this is a situation. I've got a field that's characteristic not 2. It's degree 4. irreducible, and it's got distinct roots in its floating field. So, I'm gonna let G. So let G be the Galois. So I am going to key on. So we make this notation here, transitive subgroups. S4. And this can turn out to be one of these S4, A4, D4, cyclical 4, and B. So I'm gonna key on that Klein 4 subgroup because that Klein 4 subgroup is kind of a wolf den, right? Notice that this Klein 4 subgroup is actually contained in D4 and A4, and of course S4 as well. So lemma 856. So here I'm going to use this notation that I brought over here. So let Ri denote the roots of F. Using this notation, you say explicit R3, R4, R roots of F. The group for polynomial. I am going to let alpha equal so that is my notation. 4. Theta is R1 on 3. Gamma is R1 on 4. Now, by the way, what happens when I apply the automorphisms from this group to alpha, beta, and gamma? Well, notice, for example, let's just look at alpha. The first automorphism just fixes this, right? What does the second automorphism do, right? The second automorphism swaps out 1 and 3 and 2 and 4. So 1 and 3, 2 and 4. So second automorphism takes alpha, beta, doesn't it? And the third one should third one, 1, 4, 2, 3, that turns this to a 4 and this to a 3. So, right, notice the third one leaves this one alone. Right. Oh, right. So, yeah, my bad. I don't. So the first one actually, all three of these automorphisms leave all of these on, right? For example, the second one swaps these two and swaps these two, so you get the same element. So notice these are all stabilized by all these automorphisms. So let me kind of finish my statement up here. The field K in alpha and gamma, then that field corresponds to the normal subgroup. That Klein four group intersected with Galois group. Right? Because notice that this field is fixed by the Galois actions of set V. So that corresponds to this normal subgroup V intersect G. So in particular, K, alpha, beta, gamma is Galois over K. And its Galois group is isomorphic to G mod that intersection. So I've got one more thing here. So this allows us to construct something to help us called the resolvent cubic. And this is actually why the cubic formula. How many of you have ever seen the cubic formula somewhere, right? It's a bit of a mess, right? How many of you have ever seen the cubic formula? That's death on a hot plate, right? I mean, it's this huge mess, right? And this is kind of the reason for it, because there's choices for Galois groups. Proposition 856. Let K be a field and plus x cubed. So suppose that we have this polynomial here. Just any polynomial, I guess. The resolvent cubic polynomial which is x cubed minus bx squared AC minus 4dx and then finally the constant term of resolvent is minus a squared b minus a squared d plus 4bd minus c squared. And you can check this because this is actually it's this. Okay, so let me give you the following theorem. So this is resolving cubic. This shows actually how to compute these Galois groups in this coordinate case. So theorem. Eight, 5, 8. Let K be a field and F an area whose purported with distinct roots in the splitting field. And here it is small. Polynomial. Distinct roots. And square field. And Galois group G. Let alpha, beta, gamma be the roots of the resultant cubic of F. So we compute the resolvent. We've got roots alpha, beta, and gamma, and let M be the degree. What is we let M be the degree of that extension? We have the following. Number one, M is equal to 6. If and only if Galois group is isomorphic. So if you find that this extension is of degree 6, then you have the full S4 Galois group. Number two, M is 3. That's another possibility. M is 1. Anybody want to guess on that? What is the field extension is 1? It's just isomorphic A, which is the thing we want out. We've got two possibilities left. We've got it can be either cyclic or diequal. M is 2, if and only if G is isomorphic to one of these. It's isomorphic. And you see for That'd be one of those two. And how do you make the determination on which one it is? And it's E4. If and only if F is irreducible. Um, So let's actually put this in practice. Let me work through some computation examples. Okay, so example 859. Hopefully I did some things that are fairly easy to do. I've got my result in cubic form up there, so that's going to help. Let's look first. Let's look at the following polynomials. Or x4 plus x squared. X4 minus 10x squared. Oh. Okay. So let's complete resolve it. Right? Here and my first player here, I've got A is 0. And I've got B and D. D equals 4, D equals 2. Right? So my resolvent is x cubed minus 4 x squared. Let's see, what A and C were both 0, so it's 0, and D was 2, so that's going to be minus 8x. And this is this last bit. Let's see, A and C are 0, so that's gone away. So I get plus 4BD. And so it's going to be what, 32 or something? Anybody, let's see, agree with that? Sure. 4 of the group. So that's going to be 4. So 64 minus 64 minus 32 plus 32. So this is actually x minus 4 times x squared minus 8. Which is equal to x minus 4, x minus 2 radical 2, x plus 2 radical 2. So what we're looking for this one, so I'll explain it out this way. if the degree, Q adjoin 4 and 2 plus or minus 2 radical 2 over Q. Well, 4 does nothing, right? That's already in Q. And this, so this degree is 2, isn't it? Everybody agree with that? So this brings me to the last case down here, right? That 2 is where this thing bifurcates. Okay, this should be cyclic. I'm sorry, this is either cyclic or dihedral. And that's dihedral even if and only if F is irreducible over this. Is F irreducible over, is this irreducible over, what do you think? Certainly not. Right? Right? Because you can figure out the roots of this, can't you? What are the roots of this? Well, can anybody tell me how this produces? Let's do this. This has a couple of roots. It's -4 plus or minus the square root of 16 minus 8. And that's what keep me in. It's going to be radical 2 here over 2, which is -2 plus or minus radical 2. Find that out. So this thing actually should factor as x squared minus that plus 2 plus radical 2 x squared plus 2 minus 1. See if this works. X4 middle term is going to be 4 plus 2. So the answer is no. It does. It reduces over this field. All right. So let's see 4. How about this one right here? Well, this one I have A equals C equals 0. And this time I've got B is -10 and D is 4. So this one becomes x cubed plus 10x squared. What I get out of this one. See, minus 4dx is minus 16x. And finally, 4bd is going to be minus 160. So there is your, this one has a root of, I guess, minus something, all right? Minus 1,000 plus 1,000, 165. Yep. So this has got x plus 10 times x squared minus 16. So in this case, we have Q adjoined with 4, minus 4, and 10, which is cubic. Resolving cubic actually has three rational roots. So m is 1. And the Galois group here is isomorphic. That climb 4-7, or that climb 4. Questions on that? The last one I like quite a bit because everything is 0 except for D, which is -2. That makes it easier on me. So this is x cubed plus, yeah, so this is going to be x cubed. There's no quadratic term here. D is what, -2, so that's going to be 8x. And here, well, we got a big fat 0, don't we? So the field here is cumulative 0 and radical 2i. Because you get plus or minus square root of -8. So here, once again, it means 2. So once again, here m is 2, so we have to make a decision on whether it's cyclic or whether it's dihedral. So what do we have to do? We have to look back at F here. Does x to the 4 minus 2 produce is well, let's look at the original polynomial. Oh, yeah. So original polynomial is x4 minus 2, which is x squared plus radical 2, x squared minus radical 2. And so this is like x plus I 2.4, x minus I 2.4, x plus 2.4, x minus 2. I agree with the 4 roots. Now, if this were to break down, so what do you all think? Yeah, it actually doesn't, right? Because what would have to happen, this breakdown, is you have to be able to put these back together and get all the coefficients in this field here, right? And it's close, but it doesn't quite work. So notice if you put this together, notice that none of the linear factors are in here. Do I agree with that? Because you've got the 2 and the 1, 4. That's a problem. So the only way that you'd be able to factor this over this field is to put these together in two clumps, right? Notice this clump doesn't work because you've got radical two, not radical negative two, right? Two different fields. So the only thing that you can do is put these back together this way, some form or other, or perhaps this way. But notice what happens in both cases is you get these cross terms that don't match up, right? So you're going to get x squared. Now you're going to get I plus I to the 1/4 plus 2 to the 1/4, which I think you can show is not in here. Or you get this one here with the minus sign. So this one right here. Okay. Any questions on that? Okay, this basically kind of covers things for small degree over the rationals field like that. We're going to do more applications next time. Questions? See you.